rational function. So we're going to use the graph of y is equal to x squared minus 2x minus 3, which is a simple parabola, and apply our understanding of the relationship between the graph of a function and its reciprocal to identify the characteristics of the reciprocal. So it's kind of like riding a bicycle and having training wheels. We're looking at the original function, the parabola or a quadratic, and then seeing what characteristics of it can help us determine what the reciprocal will look like. So let's first sketch the graph of the y is equal to x squared minus 2x minus 3. And determine the vertex by figuring out the zeros or x-intercepts of this function. So I'm going to factor the function first, and that means that I'm going to set y is equal to 0, because that's how you find x-intercepts or factors, and then factor using the product sum method. And if that doesn't work, of course, we can use our favorite quadratic formula. Well, maybe not all of our favorites, but some people really enjoy the quadratic formula and the discriminant. Anyway, vertex occurs at the axis of symmetry, which is between the x-intercepts or zeros. So by adding those two zeros that we find and dividing by 2, we can find the axis of symmetry. So let's go ahead and figure this out. So the original function in a factored form is x plus 1 and x minus 3. This means that the x-intercepts are -1 and +3. And vertex is going to be exactly halfway through. So we're going to add those two numbers, -1 plus 3, divide by 2. We'll end up with 1, and that is the x value of the vertex. To figure out the y coordinate, we just plug that into the equation. So we're going to substitute x with 1 and solve for y, which is -4, and that gives us the vertex. So here's that function. The x-intercepts and the vertex are shown here, and so the x-intercepts and the vertex, and there it is. So how can we use this to know what that reciprocal function looks like? Okay, so we should know from the previous lessons that the 0 of the parabola will correspond to something of the reciprocal function, and that something is the vertical asymptote. So there we go. Because of course, when we reciprocate the function, the denominator cannot be 0. So whatever used to be equal to 0, or the x-intercept, is actually going to become a restriction, and graphically that is a vertical asymptote. The horizontal asymptote, if the degree in the numerator is less than the denominator, the horizontal asymptote is y is equal to 0. So here's your shortcut, something that you should commit to memory. If the degree of x in the numerator is less than the denominator, and here we don't even have an x in the numerator, so it's definitely smaller than degree of 2 in the denominator, then the horizontal asymptote is just the along the y-axis, or the x-axis, or y is equal to 0. So the original function is listed here, the reciprocal function is listed here. What else can we figure out? Increasing and decreasing intervals. So again, we should know from the last lesson that when the original function is decreasing, the reciprocal will be doing the opposite. It'll be increasing, because reciprocal means we're making it 1 over a number. And similarly, when the original function is increasing, same thing, reciprocal will be decreasing. So here I'm showing you the range, or the interval when the original function is decreasing. That's shown in, or shaded in blue, and the original function is increasing in the area shaded by red, right? Because it's a parabola going up. So when the parabola is going downwards or decreasing, the reciprocal function will be going upwards or increasing, and vice versa. So the parabola has a minimum at 1, -4, and that's shown here. And if you think about it, the reciprocal will have, what do you think? The correct answer is the reciprocal will have a maximum, and that maximum won't be at the same coordinate. The x coordinate will be the same. X will be equal to 1. The y coordinate will be 1 over that, so it'll be -1 over 4 instead of -4. So that's going to be the maximum in our reciprocal. Okay, what else can we figure out? So when x is less than 1, the original function is decreasing, therefore reciprocal is increasing. We just said that, so that's good. And when x is greater than 1, the original function is increasing, therefore reciprocal is decreasing. So okay, we got that down. Positive and negative intervals. So this is corresponding to whether the function is above the x-axis, or positive, or below the x-axis, or negative. That, in fact, doesn't change when you reciprocate a number. So when x is less than 1 and x is greater than 4, the original, or greater than 3, the original function is above the x-axis. So that's here and here. So that means that the reciprocal function is also going to be above the x-axis. So here again, it's a little bit shaded. So when the original function is above the x-axis, the reciprocal function stays there as well. And similarly, the original function in between -1 and 3 is below the x-axis, or it's negative. The reciprocal function will also be below the x-axis or negative, and that kind of makes sense because we already identified a coordinate for the reciprocal function to be 1, -1/4, and that is below the x-axis. So that's really good. All right, so now what can we do? So what we know so far, so we know that we've got three asymptotes, 2 vertical and 1 horizontal. We know one coordinate, the maximum. We know our positive and negative intervals, and also increasing and decreasing intervals. So we got that. So reciprocal is increasing in the first 2 sections and then decreasing in the other 2. What we still need is behavior of the function around the asymptotes. So that's kind of the last thing that we're going to look at. We can also look at the y-intercept, and that's just another point to kind of have. Okay, so what can we do here? And behavior along the vertical asymptote. So if I focus on the vertical asymptote x is equal to -1, I can reach that -1 from 2 sides, either the left or the right. So the left would be here and the right would be here. So if I approach x is equal to -1 from the left, I can kind of figure out what happens to the function by subbing in a value really, really close to -1 from the left. What kind of number is that? Well, this is the notation. As x approaches, so the arrow means approaches, -1, the coordinate, and then the minus that's kind of looks like an exponent just actually means from the left side. And what number can I put in? Let's see. I'll pick -1.001. That's really, really close to -1 to the left of it. I substitute that number in for x, and I solve for y, and I get approximately 250. You can stop the video and try and do that on your own calculator and see what number you get. 250 to me means positive infinity. So I'm going to say as x approaches -1 from the left side, comma, y approaches positive infinity. And how can I show that on my graph here? Well, -1 from the left side is to the left of the asymptote. And because the y value approaches positive infinity, I'm going to put an arrow towards positive infinity, and there it is. I'll do the same thing with -1 from the right side, and I'll pick a number very close to -1 from the right or positive side. Here's the notation for it. I think I'll pick -0.999. That's very close to -1 from the right. If I plug that into my x and put that in my calculator, I get -250 for y, or approximately -250, and then I'm going to call -infinity. I'm going to write as x approaches -1 from the right side, y approaches -infinity. And how can I draw that? Well, -1 is here. From the right side means from the right of the asymptote. And if the y value approaches -infinity, that is at the bottom of the graph. So I'm going to put an arrow there. And that's my end behavior for this asymptote. Let's go ahead and do the second asymptote, which is x is equal to +3. I'm going to do the same thing. I'm going to approach x is equal to 3 from the left. So I'll pick a number really close to 3 from the left side. That number to me is 2.999. I want you to pick a number that's really close. So 2.99 works. 2.999 is better. If I plug that number in, I'll get -250. And I'm calling that -infinity. So you notice a pattern developing here. And I'll say as x approaches 3 from the left side, y approaches -infinity. On my graph here, close to my vertical asymptote, as I'm approaching -infinity, that should be, as x approaches 3 from the left, I'm going to have an arrow down on the bottom here. And sorry, I'll just sketch that properly. So that's down here. That's my arrow down here. And then I'm going to do the exact same thing, except I'm going to approach x from the right side. And that means that I'm just going to pick a number that's really close to 3 from the right. So that's going to be 3.001. Plug that into my formula or equation, and I'll end up with approximately 250. I'll write as x approaches 3 from the positive side, y approaches a big number, which is infinity. And that is going to be shown on the graph with this arrow here, which kind of popped up a little too early, but that's, I'm approaching positive infinity. And there's that second arrow that I have to draw on my own. So this is what I now need to do. The last thing is the end behavior along the horizontal asymptote. And horizontal asymptote is a little bit different than vertical. It deals with x approaches -infinity, that's on this end, and x approaches positive infinity, which is on the opposite end of the graph. So what am I going to do? I'm going to plug in x is equal to negative infinity into my equation and figure out what y is approaching. Now, what kind of number is good enough to be negative infinity? I say negative 1,000. I'll plug that into my equation, and I'll end up with 0.00000099. Well, that's really close to 0, but it's slightly bigger than 0, right? It's positive and slightly higher than 0. So I'm going to say when x approaches negative infinity, my y value is getting close to 0 from the top or from above, and that's what this plus means, because it's just slightly bigger than 0. And what will that look like on the graph? There it is. As x approaches negative infinity, the y value approaches 0, but from above, because it's slightly higher than 0. I'll do the exact same thing with positive infinity. I'll put in a number like 1,000 in for x. You can put in 10,000 if you want, and solve. I will get 0.0000, a bunch of zeros and a 1. Again, that's the same thing. I'm approaching 0 from above because the number that I get is very close to 0, slightly bigger. And I will write as x approaches positive infinity, y approaches 0 from above. And that will be shown on the graph by an arrow up here. So now I've got a lot of information here. I've got the asymptotes, I've got a point, I've got positive and negative intervals, increasing and decreasing intervals, and I also have my end behaviors. There we go. Really, I can just now connect the dots, right? I can really connect the dots. Another thing that I could do is I could find the y-intercept by plugging in x is equal to 0 into the reciprocal equation and see if I get a number that is negative, because it will then match. Here is what the Desmos graph will sketch instead of my chicken scratch here. Not so beautiful, but very accurate still. Now the question for you is, what do you think the function negative 1 over x squared minus 2x minus 3 would look like? And I hope that you can recognize that the